Hello, everybody. I hope you're all doing well. I'm going to discuss a very brief concept which is called as the idea of rolling without slip. Okay, this is in a sense a kinematic condition. Okay, so the kinematics of rolling without slip. Sometimes I also call this as rolling without sleep because that's essentially how I view it to be. Okay. All right, so what do we do here? I'm just going to consider a circular disk which is contacting a surface. Okay, so I'm just consider a circular disk, a disk contacting a surface. Okay, the surface could be stationary or could be moving. Okay, the surface itself could be stationary or in motion. Okay, there is no need for the surface to be fixed. Okay, so let's take a disk here. Let's say that here is the disk. Okay, and let's say that here is the center of the disk. I guess I can still mark the center here, and let me say that this disk has a certain radius. Let's say the radius of this disk is some r, capital R. Okay, so let's call this as capital R, and let me call the center of the disk as the point G. Okay, this is essentially the center of mass, or I guess I don't want to call it as the ground because I'm going to call the ground as G. So let me call this as the point O. Okay, and let's say that this disk is rolling, which means that this disk is performing some kind of a motion on some arbitrary surface, which I'm going to draw now. Okay, so this is an arbitrary surface. At this point, I'm assuming the surface to be a fixed surface. Okay, so I am assuming surface to be fixed, but the surface itself could be stationary or in motion. Okay, so it is not necessary that the surface be fixed. It is completely something very, very important. It is not necessary that surface be fixed. That is, for example, I could have two gears which are rolling on top of one another, because then in that situation they are not actually fixed, right? Because they're performing a relative motion with respect to one another. So that's exactly what I want to mention here. Now I'm going to assume that this is the ground. Okay, ground G, and so I see that here is the point of contact. Right, there is a point of contact, and I'm going to call that point of contact on the body. I'm going to call that point of contact as the point C, and on the ground I'm going to call that point of contact, as you might see here. I'm going to call that point, let me maybe use a different color. On the ground, that point of contact I'm going to call as the point B. Okay, so I'm going to write this down. Okay, so the disk contacts the ground at the point C, contacts ground at point C. Okay, the ground is G. So essentially we can see that C is the point on the disk, point on the disk, and then B is the equivalent point on the ground, equivalent contact point on the ground, which means that the ground contacts disk at the let me write this properly, point B. Okay, this is extremely important that you recognize that there are these two different points. Of course, at that instant in time they are touching one another, but point B is defined as a point on the ground and point C is defined as a point on the disk. Okay, And let me see if I can. I guess I cannot do that, but never mind. Probably sure I can do that. Well, that didn't end out well for me. Okay, then what I'm going to do is this is an instantaneous contact. Okay, so this is at some instant in time. Okay, so this contact that I'm defining here, so this is at some instant in time. Okay, because at the next instant in time, some other point in the disk is going to contact some other point in the ground. Okay, at next time instant. So you can almost think of this as a snapshot in time. At the next time instant, some other point on the disk is going to contact a different point on the ground. Okay, and I'm going to assume certain things. I'm going to assume that this disk is rotating in the clockwise direction. Okay, so I'm going to assume that the angular velocity of the disk is this way. Okay, I'm going to assume that the angular acceleration of the disk is also that way. Okay, so we're going to assume one more thing I'm going to write down here. So assume omega and alpha are as drawn on the figure. Okay, this is at that instant in time. Once again, at that instant in time, because what can happen is that at the next instant in time, perhaps the disk is slowing down, so its alpha can be in a different direction that is opposite to the direction of what is shown in the actual figure here. Okay, then I'm going to set up two directions. Okay, these directions are going to be marked as follows. I'm going to set up a tangential direction, okay, that is tangent to the contact. Okay, so I'm going to call this as the tangent T, and I'm going to set up a normal direction that is perpendicular to the contact. Okay, so this I'm going to call as the normal direction N. Okay, so T and N is set up at the contact point. Okay, so T is the tangent direction at the contact point, N is the normal to the contact line. Okay, so T is the tangent line at contact between disk and ground at that instant in time. Okay, and then N is normal to the tangent line at that instant. Please note you're doing dynamics, which means that things are changing instantaneously. Here today, gone tomorrow. Essentially, that's what is happening. Okay. Then we come to the criterion of definition of rolling without slip. Definition of roll without slip. Okay, so well, straight lines, come on. Well, that's better. And here is what we're going to say. Okay, so if the disk rolls without slip, the following criteria is met. If disk rolls without slip relative to the surface or the ground, the following is satisfied. Okay, what are the things that are satisfied? The first thing, at that instant in time, the relative velocity vector okay, at the point of contact is 0. Okay, so this is important. This is instantaneously what is happening. Okay, and what is the ramification of that for us? Okay, so here is the idea. At that instant in time, right, if I look at the point of contact, the point C and the point B must have a relative velocity that is 0. So velocity of C relative to B must be 0 at that instant in time. Okay, so go back to the figure and look at the figure. So let me bring the figure again here with me. Okay, I'm going to copy that. Hopefully nothing moved. And let me cut this off. We don't need the ground to be so large that it kind of, okay, so here I can say that the velocity of C relative to B is 0. Relative velocity is nothing but the difference between the absolute velocity. So VC minus VB is VC slash B, which implies that VC minus VB is equal to 0, or velocity of C is equal to velocity of B. Okay, so this is the idea of rolling without slip. This is the first criterion that has to be met. Okay, so this is fairly important. The relative velocity at the point of contact is 0. The entire velocity vector is 0. Okay, that's the first thing. Then the second thing that has to be satisfied. Okay, at that instant in time, okay, the relative acceleration vector tangential to the point of contact is 0. Okay, there are a couple of key things here. The relative acceleration vector, not the entire thing, it is only the tangential component of the relative acceleration vector is 0. Okay, so this implies that only the tangential component of the relative acceleration vector is 0. Okay, and I'm going to bring my figure once again here with your permission, because whether you like it or not, I'm going to bring it. So I want to maybe reduce the size of this guy here so that it fits into my setup. Okay, so here is the situation. And so what are the things that I can show? First of all, acceleration of C slash B can be written as acceleration of C slash B in the tangential direction, acceleration of C slash B in the normal direction. If there is rolling without slip, then acceleration of C slash B in the tangential direction is 0. Okay, so which means that the normal component of the acceleration is not 0. Okay, so this also implies that acceleration of C slash B in the normal direction is not 0. Okay, so I can expand this a little more. Acceleration of C slash B in the tangential direction is acceleration of C in the tangential direction minus acceleration of B in the tangential direction. So if I'm rolling without slip, rolling without slip implies that acceleration of Ct minus acceleration of Bt is equal to 0, or acceleration of C in the tangential direction is equal to acceleration of B in the tangential direction. Okay, the thing to keep in mind is for rolling without slip, this is the one that is true. Okay, the normal acceleration is not 0. That is something that you really have to keep in mind. And the question is, okay, why is the normal acceleration not 0? This is because if the point C does not have an acceleration normal to the point B, then the disk is never going to remove itself from the ground and let the next point come in contact. Okay, so I'm going to write this down. Okay, acceleration of C slash B in the normal direction is not 0. This is because the point C has to have an acceleration in the normal direction at that instant, so that it can actually peel off the contacting surface of the contacting surface and allow the next point to come in contact. Next point to come in contact so that the disk can roll. With time. Okay, otherwise the disk is just going to get stuck in time. If the total velocity is 0, if the total acceleration is 0, then what are you doing? You're doing a problem in statics, which means life is a little slightly easier, maybe not so much easy. If you ask my statics class, they may not necessarily tell you that, but it's still slightly better, but that is not the situation we're dealing with here. So something that you just have to keep in mind. Okay, so in summary, I'm just going to copy this main figure here. So for rolling without slip at that instant in time, okay, so in summary, okay, at that instant in time, if disk rolls without slip, then two things have to be satisfied. Okay, what are the two things? Velocity of C slash B is equal to 0, which tells me that velocity of C is equal to velocity of B. The second thing is acceleration of C slash B in the tangential direction is 0, which tells me that acceleration of C in the tangential direction is equal to acceleration of B in the tangential direction. Okay, this is the general summary. And very, very quickly, okay, so if we consider a situation, so these are the two things. Now consider the ground to be fixed. As an example case. Okay, this is not necessary. The ground need not be fixed. We are going to see problems where the ground is also going to be moving. For example, you're going to have a ball rolling on a conveyor belt, which means the belt is moving, the ball is also rolling. So this is just an example case. Then if that is the situation, then velocity of B is equal to 0, right? Because the ground is fixed. And acceleration of B in the tangential direction is also 0. This is the same reason, right? I don't want to mislead people into thinking that's something there. Copy that and then paste that here because the ground is fixed. Okay, so these are the two things. Then if I come to my figure here, okay, so I'm going to copy my figure. I'm going to copy that and then paste that here. So I'm assuming ground to be fixed. Okay, and here is what I'm trying to tell you. Okay, essentially, let me see if I can move this guy right down here. I probably can. I wanted to move that entire thing. I guess it doesn't let me, but never mind, that's okay. So if that is the case, then I know that rolling without slip, if the situation is rolling without slip and if the ground is fixed, then I can say the following. Okay, velocity of C is equal to velocity of B is equal to 0, because the ground is fixed, right? If the ground was fixed, I already knew that velocity of B was 0, and then the acceleration of B, the tangential direction was 0, and then I have acceleration of C tangential is equal to acceleration of B tangential, because it was rolling without slip. But now this is the 0 vector because the ground is fixed. Okay, so this is because the ground is fixed. And with your permission, I can also go forward a little bit more and then show you the following. How can I calculate the velocity of O? Okay, so point O and point C are points on the same body, which means that velocity of O/C relative is 0, and then I can also say acceleration of O/C relative is also 0, right? This is something that we know from basic kinematic analysis, and so I can say the following. Velocity of O is velocity of C plus omega cross or O/C. Okay, and if I do the substitutions, now I know that velocity of C is 0 because it is rolling without slip, which means that velocity of O is going to be omega cross R O/C. Look at this, R O/C. Maybe I can draw the figure once again and then show it to you here. So let me maybe just copy only this guy. Okay, so I'm going to copy that, and I'm going to bring that guy here. Okay, this is better. Let me also write the point O. So the point O was here, and the point C was somewhere here. I had the tangential and the normal direction set up, right? So this was the tangential direction, and then the normal direction was perpendicular to that, so I can maybe draw the normal direction right there. Okay, this was the normal direction. Then I had the ground, that was the contact between the ground and the disk taking place at that particular point. Okay, this was the point C on the disk, and if I now write the position vector R O/C, I'm sitting at the point C looking at the point O, which means that this is going to be R O/C. Okay, so which means if I do this and if I say that the radius of the disk is capital R, then R O/C is going to be R in the normal direction. Okay, so this is going to be capital R in the normal direction. If you want to call this as n hat, and you can call this as t hat. Okay, and you can very well see that if I make use of the right hand rule, if I go from t, I swing my arms toward the direction of n, then I can find out that the direction of rotation of this body is going to be in the k direction, and so I have a triad here. T crossed with n gives me k. Okay, where k is just a vector that is coming out of the page. I have a fixed observer who is probably sitting somewhere here. Okay, so this is I, this is j, and then this is the k direction. Okay, and this is a fixed observer who's sitting here. Let me call it as p, an inertial observer. So I can immediately see that omega is going to be in the negative k direction. So notice omega is minus omega k, and likewise alpha is minus alpha k, based on how we have assumed the disk to be rolling. Okay, so this is based on how we assume the disk to be rotating. Okay, so what I want to say is the following. Look at this. So V naught is omega cross R n hat, which is going to be minus omega k cross r n hat, which tells me, if I go back to my triad here, right, I bring my triad down, I look at the cross products. Okay, look at this. I can maybe get rid of some of these hats here. You know what I'm talking about. Okay, so if that is the case, let me remove them here too, with your permission. Okay, you can immediately see that k cross n is going to be minus t. Okay, so this is going to be minus omega r times k cross n hat. Okay, k cross n hat is nothing but minus t. Let me get rid of the hats here as well. Let me take my hats off to this problem. Okay, so this is going to be minus omega r times minus t, which means that v naught is equal to plus omega r times the direction t. Okay, so this essentially tells me that the direction of v naught is, if I copy this figure and bring it down here, okay, bear with me for one more minute and then we'll be done with this. Okay, this essentially tells me that the direction is going to be at that instant in time that. Okay, so at that instant in time, okay, v naught is along the tangential direction t drawn at the contact point at that instant. Okay, that is something that you got to keep in mind. So that's a useful idea here that you can very well see. This is r in the t hat direction, okay, or the tangential direction. And I can make use of the same idea for performing the acceleration analysis as well. Okay, we will save that for actually solving a problem, but I can make use of this. I can also say the following. I mean, if you very quickly see it, acceleration of O is acceleration of C. Then I'm going to have alpha cross R O slash C minus omega square O slash C. Then the relative term 2 omega cross V O slash C. Relative, all of those terms will cancel off for me. This term will cancel off, that term will cancel off, and then you got to be careful. Acceleration of C is acceleration of C in the tangential, acceleration A in the normal. Acceleration of C in the tangential is equal to acceleration of B in the tangential for roll without slip, but the ground is fixed, which means that acceleration of C in the tangential direction is equal to the acceleration of the fixed ground, which is equal to 0, which essentially tells me that acceleration of C is just acceleration of C in the normal direction. Okay, one more thing that I can also find out. Okay, so since the disk is rolling, acceleration of O cannot be in the normal direction. Otherwise, the disk will lift off of the surface. Will lift off the surface, or it will take off from the surface. Okay, so which essentially tells me that the acceleration of O is in the tangential direction only. So acceleration of O is something in the tangential direction only. Then acceleration of C is something in the normal direction only. Alpha, based on what I have assumed, is minus alpha in the k direction. And then I also have R O slash C as from before. This is in the normal direction. okay, which is what we had written down here, right? ROC. Okay, so ROC was in the normal direction, as you'd have seen from here. Maybe I'll bring my figure down as well. Okay, copy that and bring that down here. Okay, as you can see, and if I do the substitutions into my equations, here is what I end up getting. Acceleration of O is now acceleration of C, alpha cross RO slash C, omega square O slash C. The relative terms cancelled off because O and C are on the same body. And if I do the substitutions, this is now A naught in the T hat, AC in the N hat, minus alpha K cross R in the N hat, minus omega square is just a magnitude. Okay, it's not a vector quantity, times R in the N hat direction. Okay, K cross N hat. I have my triad, the T hat, the N hat, and then the K. This is my triad, which means that from here, this entire term is going to be minus alpha R times K cross N hat, which is going to be minus alpha R times minus T hat, right? K cross N hat, you're going against the grain, so this is going to be minus T hat, which essentially tells me A naught T hat AC N hat plus alpha times R times T hat omega square R times N hat. If I now equate the terms on right hand side and left hand side, let me not write it that way. Let me say that, okay, T hat terms on both sides, A naught is equal to alpha R. N hat terms on both sides, 0 is equal to AC minus omega square R, or AC is equal to omega square R. Okay, so which means that acceleration of O is alpha R in the T hat direction. Acceleration of C is omega square R in the N hat direction. Does this make sense? Acceleration of C has to be in the normal direction. It absolutely makes sense, right? Because if I go back to my figure, if the acceleration of C is in a normal direction, then it will allow the surface to peel off, allow the disk to peel off of the ground or peel off of the surface. And of course, I also come up with the fact that alpha times R is the angular acceleration I multiplied by the radius. This is the acceleration of the point O, which is the center of the disk. And this is the case only when the ground is fixed. Okay, so this is for a fixed ground only. Okay, and we will see situations where the ground need not be fixed, and then how these things are going to change. Okay, that we will see in the form of problems in the future. Okay, all right, so very quickly, a very brief recap or a summary of the equations. Okay, we had a brief summary written down here. So I have a disk, and then I have a ground or a surface. The disk is rolling without slip. What are the conditions that are supposed to be satisfied? At that instant in time, the relative velocity between the disk and the surface is going to be 0. And at that instant in time, the relative tangential acceleration between the disk and the surface is going to be 0. This is the criterion of rolling without slip. These two conditions always will be satisfied if the body is rolling without slip. All right. Thank you very much for your patience. I hope you're all staying safe. Take care of each other. Okay. Bye-bye.